Okay, so we showed in the previous video that if you put a conducting bar, a bar made of a conducting material, a rod, and you move the rod with a certain velocity in a region where there's a magnetic field, in this particular geometry, the rod, some charges accumulate, negative charges on one side and positive on the other, and that means that this rod behaves like a battery, and we found the potential difference across the battery, and it turned out to be BLV, the magnetic field times the length times the speed. So you can imagine that this rod is behaving as if it's like a battery with the plus side on the top and the minus side on the bottom. And that means if you put this rod in a circuit, it should produce a current, exactly like a regular battery does. So let's do that. Let's put the rod in a circuit. Now, how can you put a moving rod in a circuit? We can get rails. This is a long rail. It's a conducting rail made of conducting material, and it's not insulated. And this is also a conducting rail. And this is just a wire with a resistance from one side to the other side. Now you can put your rod on top of the rails and move the rod in this direction. And so basically now you've put the rod into a closed circuit so a current can flow. So let's look and analyze and see why the current will flow and what's happening exactly. The moving rod, we said it acts like a battery. It pumps electrons to the lower side. So that means the upper side becomes positive. Now, these positive charges and negative charges will accumulate on the surface of the wires, the same way that happened before for a regular battery, and those static charges will produce a static electric field inside the wires. Then when the electrons, the free electrons inside the wire feel the electric field, they'll move and they'll experience a force and they'll move opposite the field, and that's what makes the current flow in the circuit. So the static electric field is making the force on the charges, but the EMF in the circuit is not due to this static field. Remember, if you integrate the static force over charge or integrate the electric field, the static electric field over a closed loop, you get zero. So it's not the static electric field that's making the EMF. The EMF is coming because of the magnetic force that's pumping the charges from one side of the rod to the other. And the proof of that is if you stop the rod from moving, the charges that will just equilibrate and everything will stop. The current will just stop. So the thing that's making the current flow, the thing that's making the current sustained in the circuit is the fact that this rod is moving to the right with some velocity v. And that should be then the source of the EMF for this circuit. What I want to try to do is to show to try and find an expression for this EMF. So let's think in general. We know that total electromagnetic force on any charge is QE plus QV cross B, the electric and magnetic forces. If you divide by F, by Q, you get the force per unit charge. You have two terms that could be responsible in principle for making a force on the charges. So the definition of EMF, it's you go around the closed loop and you integrate the work. So you get the work per unit charge. So it's integration of F dot ds over Q. Now F over Q, we said it has two parts, E and V cross B. So we can substitute that. We get integration of E plus V cross B dot ds. This is the general definition of EMF due to the electromagnetic forces in the problem. We can cut this up into two terms. So we have this term with the electric field and this term with the V cross B term. Now, integration of E dot ds around a closed loop, we know this. This is the Faraday-Maxwell equation, right? So if you go around your loop and you get integration of E dot ds, what did we say it was? It was the integration of partial B by partial T dot dA. That means in this particular problem, we're putting a magnetic field that's constant. This magnetic field B is constant, it's not changing with time. So partial B by partial T is 0. So that means there's no loop integral of E around the closed loop, E dot ds. So integration of E dot ds is 0. So it's not the electric, there's no electric field being created around the loop that's making the current flow in the circuit. There's no non-conservative electric field that's making the charges flow in the circuit. Okay, so it's a kind of a subtle point. So the only term that will make the EMF then, or will result in an EMF, is this one. And so this result is actually valid for any problem where the magnetic field is constant, not changing with time, and the wires are moving. This would be the way to get the EMF for that particular problem. And you can see then it's resulting from the magnetic force term, V cross B. Now, it's a very subtle point here where we can replace the velocity of the actual charges by the velocity of the wire, and I'll put a video on that later, so just don't worry about that right now. We can just replace the V of the charges by V wire. There's just a subtle issue that the velocity of the charges is not necessarily the velocity of the wire, because the charges are also moving in the wire. So that's just a subtle point. Don't worry about it now. Let's just continue with this result, and I'll justify this later. So we showed just now that the EMF, if you have a magnetic field that's constant and the wires are moving, the EMF can be given for a closed loop, can be given by this expression. Now, I'm going to prove it, but for the general case, but you can prove that the EMF is also minus d by dt of the magnetic flux. Remember this expression, this was the expression for the EMF in the previous part when we were talking about fixed wires and changing magnetic field. And so it's really strange that you can really prove that the EMF is also equal to minus d by dt of the magnetic flux, also in this case where the magnetic field is constant and the wire is moving. We're going to prove this equivalence for the simple circuit of this problem. But in general, you can actually prove this in general, that these things are equal in general.